The sun's magnetic architecture, the engine behind every solar storm, every shimmering aurora, every silent satellite failure, is now packed into a layer just 621 miles deep. That sounds enormous. It is not. On a star whose radius stretches 432,000 miles, a body 109 times wider than the Earth, that active layer is the outermost fraction of a single % of the entire solar body. Picture the finest skin stretched over a piece of fruit. In proportion, the region where the sun stores the forces that shape our sky is thinner than that, and with every passing solar cycle, it has been getting thinner still. That last detail is the one that should keep you listening. Because the shallowing is not a fluke, it is a trend, measured across 4 consecutive cycles, spanning almost 40 years of continuous observation. The evidence has been stacking quietly for a very long time. Consider what that evidence looks like. In the closing days of 2019, an international panel of the world's leading solar physicists predicted that the current solar cycle, the one we are living through right now, would be modest. They forecast a gentle peak, a smoothed sunspot number of about 115, arriving somewhere in the middle of 2025. They were confident. They were also wrong. The cycle peaked roughly 40% higher than they predicted, and it arrived 9 months ahead of schedule. Then came the storms. A single sunspot region, an active scar on the solar surface measuring 17 times the diameter of the Earth, hurled a wave of charged matter across the emptiness of space and slammed it into our planet. The result temporarily reshaped the outer edge of Earth's atmosphere. It conjured 2 entirely new radiation belts that have no right to exist. It pushed glowing auroras down to latitudes where they have not been recorded in 500 years. And yet, not a single one of our models saw any of it coming. Here is what will quietly rearrange everything you think you understand about the star at the center of your sky. It turns out that every instrument we have relied upon for decades, every sunspot count, every measurement of the light and radio energy pouring off the solar surface, has been watching the wrong layer. The real transformation was never happening where we were looking. It was unfolding silently beneath the visible surface, in a place no telescope can photograph and no camera can reach. The change did not announce itself. It hid. And a small group of scientists, listening to the sun in a way almost no one else was, only just found it. Not by looking at it, not by measuring its light or counting its spots, but by listening to the sound of it ringing, like a struck bell, from the inside. In the late spring of 2026, researchers led by Professor William Chaplin at the University of Birmingham and Professor Sarbani Basu at Yale University published something that most people scrolled past without a second glance. They had spent nearly 40 years recording the sun's internal vibrations, and when they finally assembled the full picture, they realized the sun has been reorganizing itself from the inside out, in a way that no existing physical model predicts, and that no one had the tools to notice until now. We are going to walk through all of it tonight, slowly, carefully. The history of how we learnt to listen to a star. The instruments scattered across 6 points on the Earth that never stop recording. The storms, the records, the vanishing magnetic poles, and the strange quiet shift happening in a place we cannot see. There is no need to hold on to any of it. You do not need to remember a single number. You only need to let the story carry you. If you find something calming in the vast machinery of the cosmos, in the slow unspooling of things far larger and far older than ourselves, do me a small favor and tap the like button and subscribe if you have not already. It genuinely helps this channel keep making these long journeys into the dark for you. Now settle in. Make yourself warm and comfortable. Let's begin. To understand what changed, you first have to sit with something strange, almost impossible. No one has ever seen the inside of the sun. No telescope, however vast, can look beneath its surface. The light that reaches us leaves a thin outer skin, called the photosphere, and everything below that skin is sealed away behind a wall of blinding plasma. The Sun is a sphere with a radius of roughly 432,000 miles, and for almost the whole of human history, the enormous interior of that sphere was as unreachable as the bottom of the sea is to a candle. We could measure its light, we could feel its warmth on our skin. The engine underneath, the churning furnace that drives all of it, stayed completely hidden. And yet tonight, we have a map of that hidden interior. We know how quickly sound moves through its deepest layers. We know where the plasma streams fast and where it drifts slow. We can watch structures shift thousands of miles beneath a surface no instrument can pierce. This knowledge did not come from looking. It came from listening. Because the sun rings, not as a poem and not as a metaphor, but as a plain matter of physics. Its whole body vibrates with sound waves, a vast overlapping chorus of them, echoing through the interior in a constant, invisible hum. These are not sounds any ear could catch. The notes are far too low, and the waves are trapped inside the star, bouncing between the core and the surface, like voices sealed inside a bell. They are real pressure waves, though, moving through plasma exactly the way sound moves through the air in this room. Scientists call them P modes, short for pressure modes, because pressure is the force that carries them from one depth to the next. Here is where the idea turns beautiful. On Earth, seismologists study earthquakes not to learn about the earthquake, but to learn about the Earth itself. When a tremor sends waves rippling through the planet, those waves bend and quicken and slow, depending on what they pass through. By measuring how they arrive on the far side of the world, geologists mapped the molten outer core, the solid inner core, the hidden boundaries no drill could ever reach. They read the inside of a planet from the outside. The science that studies the sun does precisely the same thing. The earthquakes, this time, are the sun's own endless ringing, and the discipline earned its own quiet name, helioseismology, the seismology of a star. The measurement itself is astonishingly delicate. As those waves travel through the sun, they make its surface rise and fall, gently, rhythmically, like the chest of something enormous and asleep. Parts of the surface lift toward us, parts sink away. When light comes from a surface moving toward you, its color shifts by the faintest amount, the same effect that lifts the pitch of an approaching siren and drops the pitch of one speeding away. By tracking that color shift across the whole face of the sun, instruments detect the surface breathing up and down by the gentlest of motions. From those tiny movements, the entire interior is not guessed at. It is reconstructed, layer upon layer, out of the pure physics of the waves. Consider what that means. We stand tens of millions of miles away from a ball of plasma so hot and so bright that a single unshielded glance can burn the sight from our eyes. We cannot approach it, we cannot sample it, we cannot cut it open, and yet, by watching the color of its light flicker by the smallest of fractions, we can trace the path of a sound wave born deep in its belly, and from that path deduce the temperature and the density of matter we will never touch. It is a little like standing outside a sealed cathedral, in the dark, and mapping every pillar and archway within, not by seeing the stone, by listening to the way the sound moves around it. To do this, you have to listen without ever stopping. A single sound wave inside the sun can spend a long while crossing from one side to the other, and to catch the full pattern of the ringing, you cannot afford to lose the sun every time it sets. So astronomers did something patient and elegant. Beginning in the 1970s at the University of Birmingham in England, they started building small telescopes and scattering them around the globe. The network is called the Birmingham Solar Oscillations Network, and most people simply call it BiSON. It is a chain of 6 stations, set at 6 carefully chosen points around the Earth. As the planet turns and the sun slips below the horizon at one station, it is already rising into the sky at the next. The handoff is seamless. One site passes the sun to the next, around and around the world, so that at every hour of every day, somewhere on Earth, a telescope is always listening. Think of the patience in that. Every single day, for longer than many of the people listening tonight have been alive, this quiet chain of instruments has captured the trembling of the sun and written it down. No gap long enough to lose the thread. No season off. Just a steady, unbroken accumulation of the star's heartbeat, growing year by year into an archive of almost unimaginable depth. Most scientific instruments measure a moment. BiSON measures an era. And in 2026, two researchers sat down with that archive and did something no one had done before. Professor William Chaplin at the University of Birmingham and Professor Sarbani Basu at Yale University took nearly 40 years of this data and read it as a single, continuous story. Not one cycle, not one snapshot, 4 decades of the sun's inner voice, spanning 4 complete cycles of its activity, from 1987 all the way to 2025. Because the sun, for all its apparent steadiness, is not steady at all. It breathes on a slow rhythm, swinging from storm to calm and back to storm across the better part of a decade. It grows restless, its face darkening with the cool blemishes we call sunspots. And then it settles again, its surface smoothing to a clean and quiet glow before the restlessness returns. Each of these long swings is called a solar cycle, and scientists number them in the order they occur. The recent ones carry the numbers 22, 23, 24, and 25. And the cycle numbered 24, the one that finally ended in 2019, was a remarkably feeble thing. It was the weakest solar cycle in 100 years. At its height, it reached a smoothed sunspot number of only 114, against a long historical average of 179. By its own ancient standards, the sun had gone pale. The quiet, though, had been settling in for longer than that. The lull that opened cycle 24 in the years 2008 and 2009 was the longest and quietest solar minimum ever recorded. For long stretches, the sun's face was utterly blank, not a single spot. Anyone watching only the surface might have believed the star was drifting towards some deep and lasting sleep. But the surface, as always, was not the whole truth. When Chaplin and his colleagues later listened back to the sound waves from that deep minimum, they found something the empty face had hidden. The interior carried a mark. The helium buried in the outer layers rang out with a stronger signal than in earlier minima. Sound moved faster through the outer plasma. The gas pressure ran higher, and the temperature slightly warmer than the calm exterior implied. The silence on the outside had not meant silence all the way down. As Chaplin put it, deep quiet minima can leave a measurable internal fingerprint. Then, when cycle 24 finally exhausted itself and sank toward its close in 2019, the sun fell into another deep trough. The minimum between cycle 24 and cycle 25 dropped to a smoothed sunspot number of just 1.8, one of the deepest values in the entire modern record. Twice now, within a single human lifetime, the star had gone almost completely quiet on its surface. And twice now, the deeper story was written not in what the sun showed us, but in what it withheld. This is the shape that will return again and again tonight. The surface says one thing, the interior says another. What we can see is not what is actually happening. For most of the last century, we had no choice but to trust the surface, because the surface was all we could measure. The spots, the flares, the visible skin of the star. Helioseismology changed that, slowly, patiently, over the course of decades. It handed us a second pair of eyes that look not at the light but through the sound. And when those eyes turned toward nearly 40 years of the sun's inner ringing, they began to notice something that no one had ever been able to see before. The bond between the star's hidden rhythm and its outer face was not fixed at all. It was quietly, steadily coming apart. To understand what those second eyes actually saw, you first have to understand what they are. They are not eyes in any familiar sense. They are 6 telescopes scattered deliberately around the world, and they have been listening to the sun since the 1970s. The network carries a quiet, unglamorous name. It is called the Birmingham Solar Oscillations Network, and the idea behind it is beautifully simple. The sun never stops ringing. Any single observatory, though, can only watch it for part of a day before our planet turns its face away into night. So the astronomers did something patient and deliberate. They placed their instruments at intervals around the globe, so that as one station rotated into darkness, another was already turning toward the light. The sun is always in view of at least one of them. The listening never stops. Consider what that means. For decades, without a single long pause, this chain of 6 eyes has been recording not the brightness of the star, and not its color, but its motion. The gentle rising and falling of its surface. The whole visible face of the sun swells outward and sinks back, over and over, like the skin of an enormous drum that has just been struck and cannot stop trembling. These motions are tiny compared to the sun itself. They are almost unimaginably small against a body so vast. Yet they are utterly regular, and regularity is a language. A star that vibrates in fixed patterns is a star that is telling you about its own insides. This is the heart of the technique, and it deserves to be said plainly. It is called helioseismology, and the name contains its whole meaning. Seismologists study earthquakes. When the ground shakes, waves travel through the body of the Earth, and by measuring how those waves arrive at stations across the surface, geologists can map layers of rock they will never see, thousands of miles beneath their feet. Helioseismology does exactly the same thing with the sun. The sun is filled with sound, not sound that travels through air, but pressure waves rolling through the hot dense plasma of the star, bouncing off its inner layers, bending as they pass through regions of different temperature and density. These are called P-mode oscillations, pressure waves, the sun's own internal music. They ring through the star and return to the surface, and when they reach it, they nudge that surface up and down by a whisper. That whisper is what the network measures. The instruments read it through something called Doppler velocity, the same principle that makes a passing siren drop in pitch as it moves away from you. As the surface rises toward the telescope, the light it emits shifts by a hair. As it sinks away, the light shifts back. By tracking those shifts, precisely, patiently, for nearly 40 years, the network turns the sun's silent, trembling into numbers. And within those numbers live the frequencies of the sound, the exact pitches at which the star is ringing. The researchers did not listen to only one pitch. They separated the sun's music into 3 distinct frequency ranges. And this distinction is not a technical footnote. It is the whole reason the discovery was possible. Different frequencies of sound reach different depths inside the star. Some waves stay shallow, skimming just below the surface. Others plunge deep before curving back up. So by comparing how the different pitches behave, scientists can read the sun the way you might read the rings of a tree, layer by layer, each depth telling its own part of the story. The high frequencies carry news from just beneath the skin. The lower ones speak from farther down. Together they form a portrait of a star's interior that no camera could ever take. This was the instrument that Professor William Chaplin at the University of Birmingham and Professor Sarbani Basu at Yale University turned toward nearly 40 years of accumulated data. 4 solar cycles from 1987 through 2025. Cycles 22, 23, 24 and 25. Each one a rising and falling tide of magnetic activity. Each one recorded not only in the visible spots on the surface, but in the changing pitch of the sound below. It is one thing to watch a single storm season on the sun. It is another thing entirely to hold 4 of them in your hands at once, laid side by side, and to ask whether the star is behaving today the way it behaved a lifetime ago. To understand why that question matters, return for a moment to those quiet years, the deep minimum that stretched across 2008 and 2009. On the surface, it looked like almost nothing, a blank star, spotless for days and weeks on end. the kind of stillness a casual observer would call empty. But the interior remembered. When scientists examined the sound waves recorded through that silence, they found the star's inner voice had changed. The signals from the layer of helium beneath the surface had grown stronger. The sound moved faster through the outer regions, the gas pressure ran higher, and the temperature sat slightly warmer than it had in earlier quiet spells. None of this showed on the face of the sun. All of it was written underneath. As Bill Chaplin put it, deep quiet minima can leave a measurable internal fingerprint. Sit with that phrase for a moment. A fingerprint. The idea that stillness on the surface is not the same as stillness within, that a sun which appears to have gone to sleep may in fact be rearranging something in its depths, leaving a mark that only sound can find. This is not the behavior of a simple furnace burning at a constant rate. It is the behavior of something structured, layered, and quietly alive with change. The quietest years were not the emptiest years. They were the years when the deepest story was hardest to see and easiest to miss. And this is where the 4 decades of listening delivered their most unsettling result. When Chaplin and Basu compared the sun's internal frequencies against its outward signs of activity across all 4 cycles, they found that the relationship between the two was not holding steady. The bond between what the sun sounds like inside and what it shows on its surface had shifted, and shifted significantly, at some point after cycle 23. For as long as anyone had assumed, the inside and the outside of the sun moved together. The louder the interior, the busier the surface. That link was supposed to be a constant, a fixed exchange rate between the hidden star and the visible one. It was not. It was drifting. They could even estimate when the drift began. Not recently. Not in the last year or two, when the current cycle grew strange enough to draw attention. The change traces back to around 2005, and here is the detail that turns a scientific finding into something closer to a chill. 2005 was almost 2 full solar cycles before any instrument on Earth was sensitive enough to notice the shift as it was happening. The sun had already begun to reorganize the relationship between its interior and its surface, while the world below was still measuring it the old way, still trusting the spots, still reading the visible skin as though it told the whole truth. The evidence had been gathering quietly, cycle after cycle, waiting in the recorded sound for someone to assemble enough of it to see the pattern. By the time we could finally hear the change, it had already been underway for the better part of 2 decades. To understand what that recorded sound actually revealed, you first have to understand how anyone could listen to a star at all. You cannot place a microphone on the surface of the sun. You cannot lower an instrument into its depths. Nothing we build could survive the approach, let alone the descent. And yet the interior of the sun is not silent. It is, in a very real and measurable sense, ringing. The whole body of the star vibrates with sound, pressure waves that rise and fall through its layers, waves that have been echoing inside it for as long as it has existed. We simply had to learn how to hear them. The technique is called helioseismology, and the name tells you exactly how it works. Seismologists study earthquakes not because they can see into the earth, but because sound waves passing through the planet bend and slow and speed up depending on what they travel through. A wave that crosses dense rock behaves differently from a wave that crosses molten metal. By recording those waves at the surface, seismologists reconstruct a picture of a place no human will ever visit. Helioseismology does the same thing with the sun. The sound waves are already there, generated by the roiling turbulence of the outer layers, bouncing endlessly through the interior. All we have to do is measure them where they surface. And they do surface. Every one of those internal sound waves, on reaching the visible face of the sun, pushes that surface outward by a tiny amount and then lets it fall back. The entire face of the star breathes, not as a single motion, but as millions of overlapping ripples, each one the fingerprint of a wave that has traveled a specific path through a specific depth. To an ordinary telescope, none of this is visible. The surface looks still, but the light itself carries the secret. As a patch of surface rises toward us, the light it emits is shifted very slightly toward the blue. As it sinks away, that light shifts toward the red. This is the Doppler effect, the same phenomenon that stretches the pitch of a siren as it passes you on the street. The Birmingham Solar Oscillations Network reads those shifts. It measures the velocity of the sun's surface as it rises and falls, and from that velocity it reconstructs the sound. Consider what this means. We are not looking at the sun in the way you look at a photograph. We are listening to it in the way you might press your ear against a wall and infer the shape of the room beyond. The waves that reach the surface have each dived to a different depth before returning. The lowest tones probe the deepest interior. The higher tones stay nearer the top, turning back before they ever reach the core. By separating the sound into distinct bands of pitch, the researchers could ask the interior different questions at different depths. The Birmingham and Yale teams worked across 3 distinct frequency ranges, 3 separate windows into the star, each one sensitive to a different layer of the whole. But raw sound is a chaos of overlapping voices, and the individual notes have to be pulled out of that noise one at a time. This is where the mathematics enters. The researchers applied a method known as Bayesian fitting to the Doppler velocity data, a statistical technique that takes an enormous tangle of measurement and asks, patiently, which underlying pattern best explains what was actually recorded. It does not guess. It weighs the evidence, refines the estimate, and returns the most probable structure hidden inside the data. Applied to the P-mode oscillations, the global pressure and sound waves that fill the sun, this method turns a wall of noise into a set of precise frequencies. And it is in those frequencies, tracked across nearly 40 years and across 4 consecutive solar cycles, that the change lives. Here is the problem. When the researchers followed those frequencies from cycle 22 through cycle 23, then into 24, then into the strange cycle 25, they found that the sun's magnetic activity was not staying where it had always been. It was moving. With each successive cycle, that activity was being squeezed into an increasingly shallow layer just below the visible surface, not spreading, not deepening, compressing, rising toward the skin of the star and thinning as it rose. And by the most recent measurements, the layer holding this magnetic activity had been driven to within approximately 1,000 kilometers of the photosphere, the visible surface itself. That is roughly 621 miles. To feel how thin that is, you have to hold it against the size of the thing it sits upon. The sun has a radius of about 432,000 miles. 621 miles, measured against 432,000, is the outermost fraction of a single % of the entire solar body. Picture the sun shrunk to the size of a large beach ball. The layer now holding its magnetic activity would be thinner than the coat of paint on the ball's surface. Everything that makes the sun a magnetic star, everything that drives its spots and its flares and its storms, is being pressed into a skin so shallow that on any honest scale drawing it would vanish beneath the width of the line marking the edge. The obvious explanation, the one almost anyone would reach for first, is that the sun is simply weakening. A star running low on magnetic strength might well show a fainter, shallower cycle, its activity fading toward the surface as the engine beneath it winds down. It is a clean idea. It fits the intuition that cycle 24 was feeble and cycle 25 was supposed to be feeble too. And it is, according to the people who did the work, wrong. Professor Sarbani Basu of Yale addressed this directly. This trend, she said, cannot be explained simply by weaker magnetic fields. Instead, it indicates a structural reorganization of how the sun's magnetic activity is stored beneath the surface. Not a dimming, a rearrangement. The star is not losing its magnetism, it is changing where it keeps it. Professor William Chaplin of Birmingham put the finding in equally plain terms. They had uncovered evidence of systematic changes in the solar activity cycle. And crucially, he said, magnetic activity is becoming more tightly confined near the surface with each cycle. Read those two statements together, and the shape of the discovery comes clear. This is not a single anomalous reading. It is a direction. 4 cycles pointing the same way, across 40 years of continuous listening. The magnetic life of the sun migrating steadily upward toward its own visible face, cycle after cycle after cycle. And this is where the strangeness sharpens into something genuinely difficult. Because if you had only looked at the sun's surface, only counted its spots, you would have concluded that cycle 25 was a modest affair. The sunspot counts pointed that way. So did another traditional gauge, the 10.7 centimeter radio flux, a measure of the radio energy the sun pours out at a specific wavelength, long trusted as a proxy for how active the star truly is. Both of these surface indicators told the same quiet story. A middling cycle. Nothing to alarm anyone. The sound told a different story. The high-frequency internal data, the deep register of the sun's own ringing, showed a cycle that was comparably strong to the cycles before it. Not modest at all. The energy was there. It had not weakened. It simply was not expressing itself the way it always had. Was not surfacing as spots. Was not announcing itself in the radio glow. It was present, and it was powerful, and it was hidden, trapped below the visible surface in that ever-shallowing layer, held back from the face of the star that we have spent 4 centuries watching. The sun looked calm on the outside while carrying a full charge underneath. The skin lied, the sound did not. Consider what it would mean to live your whole life reading one signal, trusting it completely, building your forecasts and your models and your sense of safety upon it, and then to discover that the signal had quietly detached from the thing it was supposed to represent. For 400 years, sunspots have been humanity's window into the sun's temper. Galileo watched them cross the disk. Generations of astronomers counted them, catalogued them, learned to read the rise and fall of their numbers as the pulse of the star. That pulse was our early warning, our best guess at when the sun would rage and when it would rest. And now the interior evidence suggests that the pulse and the star have begun, slowly, to keep different time. You can still count the spots, they are still real, but they are no longer telling you the whole truth about the power gathering beneath them. There is a particular kind of unease in that, not the sharp fear of an immediate threat, but the slower, deeper discomfort of realizing that a thing you thought you understood has been quietly becoming something else while you watched the wrong part of it. The sun did not warn us, it simply changed, in a place we could not see, using a language we had only just learned to hear. And the more precisely the researchers listen, the more they confirm that this is no fluke of a single strange cycle. It is a persistent direction, written into 40 years of sound, pressing the fire of a star toward the thin bright edge of its own surface, and holding it there. To understand how anyone could possibly know the depth of a magnetic layer buried inside a star, you first have to understand what the researchers were actually measuring. Not the light of the sun, not its heat, not the spots on its face. They were measuring its sound. The surface of the sun is not still. It heaves, it rings. Across its entire face, the outer layers rise and fall in a slow, ceaseless shimmer, millions of separate oscillations overlapping into a single planetary chord. These are pressure waves, sound waves, born in the churning convection just beneath the surface, and trapped inside the body of the star like a struck bell that never quite stops ringing. The sun is singing. It has been singing for 4.5 billion years. Only in the last several decades have we finally learned how to listen. The instrument that listens is BiSON, and what it records is motion. As those internal sound waves reach the surface, they push the visible gas gently toward us, and then gently away, and that motion shifts the color of the light by an almost imperceptible amount. This is Doppler velocity data, the same effect that raises the pitch of a passing siren, only measured here in the faint reddening and bluing of sunlight. The researchers do not see the waves, they see the breathing of the surface, and from that breathing they reconstruct the waves that caused it. It is a little like standing outside a sealed cathedral and reconstructing the shape of every pillar inside, from nothing but the way the organ music leaks through the walls. Here is the part that turns sound into a map. A wave born at the surface does not stay at the surface. It plunges downward into the sun. And because the deeper layers are hotter and denser, the wave bends, curving back up toward the surface like a swimmer arcing off the bottom of a pool. A low, slow wave dives deep before it returns. A high, fast wave turns back near the top. Each frequency then samples a different depth. This is why the researchers separated the sun's song into 3 distinct frequency ranges. Not for convenience. Each range is a different sounding line dropped to a different level inside the star, and together they let the team feel the interior the way seismologists feel the inside of the Earth, by watching how earthquake waves bend around its hidden core. To pull a signal that faint out of 40 years of shimmering data, the team led by William Chaplin at the University of Birmingham and Sarbani Basu at Yale University used what is called Bayesian fitting. In plain terms, it is a disciplined way of asking which interior structure would best explain the exact tones the sun is producing, while honestly accounting for everything that remains uncertain. You do not simply read the answer off a dial. You test every plausible version of the sun's interior against the music, and let the most consistent one rise slowly out of the noise. It is painstaking. It is unglamorous. Yet it produced one of the strangest results in the modern study of our star. The result was a trend. Across solar cycle 22, then 23, then 24, and now 25, the layer where the sun's magnetic activity is stored has been growing shallower. Not holding steady, not wandering randomly. Shallower in the same direction, cycle after cycle after cycle. With each pass, the fire is squeezed into an increasingly thin sheet just below the visible surface, until in the present cycle it sits confined within roughly 1,000 kilometers of the photosphere. That is about 621 miles. On a star whose radius stretches more than 400,000 miles, that confining layer is thinner, in proportion, than the peel on an orange. The entire magnetic engine of a body large enough to hold our whole world many hundreds of thousands of times over has been pressed into its outermost skin. The obvious explanation, the one almost anyone would reach for first, is that the sun's magnetic fields are simply getting weaker. A dimming furnace. A star quietly winding down. It is a clean story, and it is wrong. The researchers considered it directly and ruled it out. As Sarbani Basu put it, this trend cannot be explained simply by weaker magnetic fields. Instead, she said, it indicates a structural reorganization of how the sun's magnetic activity is stored beneath the surface. Read that slowly. The energy has not faded. It has moved. The architecture itself, the deep geometry of where the star keeps its fire, is being rebuilt while we watch. Not a dimmer flame, but the same flame relocated to a place it has never before been held. This is where the discrepancy that opened this chapter finally clicks into focus. Look at the sun's surface by the traditional measures, the sunspot counts and the 10.7 centimeter radio flux that scientists have trusted for generations. And cycle 25 reads as merely moderate. A respectable cycle. Nothing to alarm anyone, but listen to the high-frequency sound waves, the ones that turn back just beneath the surface, and they report a cycle comparably strong to the powerful ones that came before. The two instruments disagree, and they disagree because they are looking at different depths. The surface is underreporting. The energy is there. It is simply held below, in that thin compressed layer, doing its work out of sight of the very sunspots we have always used to take the sun's measure. For 40 years the network has recorded this. 4 consecutive cycles. Not a single anomalous season. Not one freak reading that might be smoothed away as instrument drift or bad luck. A directional signal, persistent across 4 decades. All of it pointing the same way. In science, a single strange result is a question. A trend that holds for 40 years and 4 cycles is something much heavier. It is a fact about the sun that has to be explained rather than explained away. To sit with the length of that record is its own small vertigo. 40 years is not an abstraction. It is a person born around the time the network first switched on, grown now into middle age, having lived an entire life while the star performed this slow migration one cycle at a time. If you had asked a solar physicist in the 1980s where the sun kept its magnetism, they would have given you an answer, and it would have been the best answer available, and it would no longer be quite true. The sun did not break any law we know. It did something subtler. It drifted, patiently, across 4 cycles and 4 decades, from one internal arrangement toward another, so gradually that no single year would have betrayed it. Only the whole span, laid end to end, reveals the direction. Not a jolt, but a tide. Consider what that means for you. Standing on a planet that orbits this star at a distance of 93 million miles, close enough that its ordinary light warms your skin on a clear afternoon. Everything that reaches you, the sunlight, the space weather, the storms that ripple through the sky, is shaped by processes that begin far below the surface you can see. That hidden machinery, the part you cannot photograph or point a telescope at, has been quietly rearranging itself for longer than most people watching were aware there was anything to rearrange. You have felt only the surface. You have always felt only the surface. Beneath it, the star has been becoming something the textbooks did not describe, and the first honest report of that change arrived only a handful of months ago. There is a strange intimacy in it. We have listened to the sun sing for half a lifetime, and only now heard the melody begin to shift. The waves were always carrying the message. We simply lacked the ears. Now that we have them, the song tells us that the calm, familiar star we have measured for centuries has, in the one place we could never reach, started to keep its fire somewhere new. Consider what this means for the people whose task is to see it coming. There is a small community of scientists whose profession is the forecasting of the sun. They watch the sunspots. They track the magnetic fields at the surface. They feed decades of measurement into models refined across generations. And from those models they issue a prediction, a single number that tells the world how loud the coming cycle will be. That number is not an academic curiosity. It shapes how satellites are built, how power grids are hardened, how astronaut missions are scheduled, how airlines plan their routes across the poles. In the winter of 2019, that community gathered to make its call. In December of 2019, an international panel released its official forecast for the cycle about to begin. The panel was convened by the National Oceanic and Atmospheric Administration, by NASA, and by the International Space Environment Services. It predicted that solar cycle 25 would reach its peak at a smoothed sunspot number of 115, give or take 10. It predicted that this peak would arrive in July of 2025. In plainer terms, the panel expected the coming cycle to be quiet, not silent, but modest. Roughly the same gentle character as the cycle that had just ended, the one that had been the weakest in 100 years. This was not a reckless guess. It was the considered judgment of some of the best solar physicists alive, drawing on the deepest quiet minimum in the modern record. Everything they could measure pointed the same direction. The sun had just passed through one of the stillest stretches it had shown in a century. The surface was calm. The sunspot count had fallen almost to nothing. If the recent past meant anything at all, the near future should have resembled it. So the forecast promised more of the same. A weak cycle following a weak cycle, a tired star settling into a long, low murmur. The sun did not cooperate. It did the opposite. And it did the opposite with a force that no model had anticipated. The first sign came early. Where the panel had imagined a slow, hesitant awakening, the star did something else entirely. In that opening year, it logged 101% more spots per day than the previous cycle had managed in its own first year. Not a few percent more, not a modest overshoot, more than double in the very first stretch of a cycle that was supposed to be faint. the climb continued. The unsmoothed monthly sunspot number, the raw tally of dark blemishes crossing the visible face of the sun, rose past the predicted ceiling and kept rising. In August of 2024, that number reached 216. The forecast had spoken of a peak near 115. The reality very nearly doubled it. 2 months later, in October of 2024, NASA and the National Oceanic and Atmospheric Administration made it official. They declared that the sun had reached solar maximum, and they placed that maximum at a smoothed sunspot number of 160.8. Read those two numbers side by side. The prediction was 115. The measurement was 160.8. The cycle arrived roughly 40% stronger than the finest forecast humanity could produce. It also arrived early. The panel had marked July of 2025 as the likely peak. The sun reached its maximum 9 months ahead of that date, in the autumn of 2024, while the calendars still read a full year too soon. There is a particular kind of humility in a miss like this. It is not the humility of a careless mistake. It is the humility of doing everything correctly and still being wrong. The models were sound. The data were real. The scientists were among the most capable in their field. The sun simply refused to behave the way its own recent history said it should. The overshoot was not a single spike that quickly faded. It persisted. By December of 2025, well past the declared maximum, solar cycle 25 was still averaging 31% more sunspots per day than the cycle before it. The star was not merely louder at its peak, it was louder across its whole span, sustaining an intensity the forecast had never contemplated. Month after month, the sun kept producing more than it was supposed to, as though working from a different script than the one we had written for it. To feel the full strangeness of this, hold two facts together in your mind. The cycle that came before, solar cycle 24, was the weakest in 100 years. Its own peak had climbed only to a smoothed sunspot number of 114, far below the long historical average of 179. The minimum that followed sank to a smoothed sunspot number of 1.8, among the deepest ever recorded, a stretch of near total quiet. By every surface measure, the sun was fading. It looked like a star winding down. Out of that stillness, out of that apparent exhaustion, came a cycle that overshot every prediction and refused to slow. Imagine you had been handed only the surface record, only the sunspot counts, only the calm century-low cycle and the record-deep quiet that followed it. If that was all you were given, you would have made exactly the forecast the panel made. You would have looked at the evidence and concluded, reasonably, sensibly, correctly by every rule available to you, that the next cycle would be gentle too. And you would have been wrong by 40%. The surface told a story that the surface itself could not have known was incomplete. Here is where the two threads begin to twist together. The forecast was built entirely on what could be seen, the sunspots, the magnetic fields at the surface, the visible history of the star. But we now understand that something the forecast could not see had already been underway for a very long time. The internal reorganization, the slow migration of magnetic activity toward that shallow layer near the surface, did not begin in 2019. It did not begin with this cycle at all. The evidence points back to around 2005. Sit with that date for a moment. Around 2005, the relationship between the sun's inner sound waves and its outer activity had already started to change. That was almost 2 full cycles before any instrument was sensitive enough to notice. It means that when the panel gathered in the winter of 2019 to forecast the coming cycle, the sun's interior had already been quietly rearranging itself for roughly 15 years. The scientists were reading the surface with enormous care. Beneath that surface, in a place their instruments could not yet interpret, the star had been becoming something else for a decade and a half. This is the unsettling symmetry at the center of the story. On the surface, a prediction failed by 40%, and no one could fully explain why. Below the surface, a structural change had been building since before the failed prediction was even conceived. The two are almost certainly connected. The energy the forecast expected to appear as sunspots may have been present the entire time, comparably strong to earlier cycles, simply held somewhere the counting could not reach. Think about what that implies for everything we believed we understood. If the interior has been changing for 15 years without a single warning reaching the surface record, then the failed forecast is not an isolated error to be quietly corrected next time. It is a signal. It suggests that the tools we trusted to read the sun were measuring the wrong layer, or at the very least an incomplete one. We built our forecasts on the surface, because the surface was all we could measure with confidence. The honest answer, the one the researchers themselves offer, is that no existing physical model predicted this confinement, and none can yet fully explain it. The surface has betrayed our expectations once already. The depths have only begun to speak. Consider the numbers themselves, not as abstractions floating in a report, but as a record of exactly how far the forecast fell. The panel had spoken of a smoothed sunspot number of 115, give or take 10, arriving in July of 2025. The sun did not wait until July. It did not stop at 115. The raw monthly sunspot number climbed to 216 in August of 2024, and when NASA and the National Oceanic and Atmospheric Administration finally declared that the peak had come, they placed the smoothed figure at 160.8 in October of that same year. This was no small miss. It stood roughly 40% above the predicted ceiling, and it arrived a full 9 months ahead of the date the experts had marked. To feel how unusual that is, consider what such a forecast actually represents. It was not a single guess made by one person on a quiet afternoon. It was the shared judgment of an international panel, built on decades of careful observation, refined against every cycle that had come before. These are among the most studied predictions in all of solar science, and still the sun overran them, not by a rounding error, not by the margin the panel had honestly allowed for, by something closer to half again, as much as the highest number they were willing to write down. There is a temptation, when a forecast fails, to treat the failure as bad luck. A single cycle is a single sample. Perhaps the sun simply rolled the dice and landed on an unlikely face. But the record does not read like a single unlucky throw. It reads like a pattern, steady and building, visible in more than one measurement. Consider the rate at which the spots appeared. By December of 2025, solar cycle 25 was averaging 31% more sunspots per day than the cycle before it. 31% is not a subtle difference. If two neighbours kept gardens of the same size, and one grew nearly a third more flowers every single day, month after month, you would stop calling it chance. You would start looking for what was different in the soil. And the difference showed itself early. In its very first year of life, from December of 2019 through November of 2020, Cycle 25 produced 101% more spots per day than Cycle 24 had managed across the same opening stretch. More than double. From its first breath, this cycle was behaving like a different kind of star than the forecast described. The excess was not something that crept in near the peak. It was present at the very beginning, when the numbers were still small and easy to overlook. Now hold that acceleration against what came just before it, because the contrast is where the strangeness truly lives. Solar Cycle 24, the cycle that ended in December of 2019, was the weakest in 100 years. Its peak reached a smoothed sunspot number of only 114, against a long historical average of 179. That is a cycle that came in far below the ordinary. And the quiet did not stop at the peak. The minimum that followed sank to a smoothed sunspot number of just 1.8, one of the deepest and stillest troughs in the entire modern record. Sit with that figure. 1.8. For long stretches, the face of the sun was simply blank, day after day, a smooth and featureless disk. Many observers who had spent their careers counting spots found themselves with almost nothing to count. It was, by every surface measure available, a sun that had gone quiet, not resting for a season, but quiet in a way that stretched on longer than almost anyone alive had witnessed. And from that stillness, from the deepest modern minimum, a cycle that outran its own forecast by 40% and doubled its predecessor's early output. The weakest cycle in a century gave way not to another weak cycle, as the panel reasonably expected, but to one of the most vigorous starts in living memory. The quiet did not predict more quiet. The quiet, it turns out, predicted almost nothing at all. Here is the problem. Every instinct we have tells us that a weak system stays weak, that a quiet engine idles, that stillness is a reliable sign of low energy. We reason this way about nearly everything in our ordinary lives, and most of the time the reasoning holds. But the sun does not appear to obey it. The stillness of cycle 24 was not emptiness. It may have been something closer to compression, energy gathering in a place the surface could not report. This is where the helioseismic evidence and the failed forecast fold into a single story. Remember what the internal sound waves revealed. Remember that the relationship between the sun's deep oscillations and its surface behavior had already begun to shift around the year 2005. That drift was underway long before the panel gathered in December of 2019 to write its prediction. For roughly 15 years, the interior of the sun had been quietly rearranging the way it held its magnetic activity, pressing it into ever shallower layers, while the surface offered only the ordinary clues of spot counts and radio flux. So when the panel looked at the surface and saw a weak, quiet star settling toward another modest cycle, they were reading a real signal. It simply was not the whole signal. The face of the sun told them one thing. The body of the sun, had they possessed a tool sensitive enough to hear it in that moment, was already telling a different story. The forecast was not wrong because the scientists were careless. The forecast was wrong because it was built on the only layer we could measure, and that layer had quietly stopped being the whole truth. Think about the position this leaves us in. We predicted a modest cycle and received an unusually strong one. We measured a deep and lasting quiet, and it gave birth to vigor. We trusted the surface, as we always had, and the surface delivered a maximum 40% higher than our best consensus, 9 months before we thought to expect it. Each of these facts, taken alone, might be filed away as a curiosity. Taken together in the same cycle pointing in the same direction, they stop feeling like curiosities. They begin to feel like a warning that our reading of the sun has been incomplete in some fundamental way. And the warning does not end with the counting of spots. A cycle this much stronger than forecast is not merely a mark on a chart. Sunspots are the visible knots of the sun's magnetic field, and a sun that produces far more of them than expected is a sun holding far more stored magnetic energy than the models assumed. That energy does not stay politely bottled beneath the surface forever. It finds release. It reaches outward. And when a cycle that no one predicted decides to release the energy it was never supposed to have, the consequences do not remain confined to a diagram in a research paper. They travel the long, cold distance to Earth. They arrive here, in the air above our heads and the machines we have flung into orbit. Consider what it means to be surprised by a star, not startled by a distant flicker at the edge of a telescope, not puzzled by a faint reading from some object halfway across the galaxy, but genuinely surprised, in real time, by the nearest and most studied object in our sky. The sun is not a faint smudge at the limit of instrumentation. It is the thing we see every clear morning, the thing our entire species has watched for as long as there have been eyes to watch. We have measured it for centuries. We have counted its spots since the age of the first telescopes. And still, in the third decade of the 21st century, it did something our finest collective judgment did not see coming, and something our physics still cannot fully explain. That is the true weight of the shattered forecast. It is not the embarrassment of a wrong number. Numbers are wrong all the time, and science absorbs the correction and moves on. It is the deeper implication underneath. If the sun could hide this much strength beneath a quiet face, if it could reorganize its inner structure for 15 years without a single unmistakable warning reaching the surface, then we are forced to admit how thin our understanding truly is. We know the sun's outermost skin. We are only beginning to learn its depths. And a star that can surprise us this completely from within is a star that can reach out to touch us in ways we are only now learning to anticipate. That reach is not a matter of theory, it has already happened. And it happened while the ink on the failed forecast was barely dry. The reach came in the second week of May, in the year 2024. It came from a single scar on the visible face of the sun, a region catalogued with the plain and forgettable designation 3664. There was nothing plain about it. That one active region had swollen to an area 17 times the diameter of Earth. Try to hold that in your mind for a moment. Not 17 times the area of some country, not 17 times the width of an ocean, 17 times the entire diameter of our planet, a single magnetic wound wide enough to lay more than a dozen Earth's edge to edge across its span. And it was awake. For most of human history, a sunspot that large would have been invisible to us, or worse, a bad omen scrawled across the sky with no explanation attached. We would have seen the lights and felt the fear and understood nothing. We are not that species anymore. We watched this one form. We tracked its growth day by day. And when it finally fired, we measured the consequence with instruments that had been waiting patiently for precisely this moment. That measurement carries a name worth understanding, because it is the number that tells us how deeply the sun reached toward us. Scientists track the strength of a geomagnetic storm using a value called the Disturbance Storm Time Index, a measure of how severely the sun has deformed the Earth's own magnetic field. In quiet times, that number hovers near zero. A serious storm might push it down toward -100. During the storm of May 2024, the index plunged to somewhere between -412 and -518 nanoteslers at 3 o'clock in the morning, Universal Time, on the 11th of May. It was the deepest plunge in more than 20 years. This storm has a name of its own. Scientists came to call it the Gannon storm, after the physicist Jennifer Gannon, a researcher of space weather, whose work helped the field understand the very kind of event that would come to carry her name. It was the first storm in over 2 decades to reach the highest category on the scale used to classify these events, the level scientists simply call severe. Not strong, not merely intense, severe. The very top of the ladder, a rung that had gone unvisited since a time when most of today's satellites had not yet been built. Here is where everything you have heard so far draws together. Remember the central mystery. The surface of the sun had been telling a modest story. The sunspot counts, the gentle radio glow, the quiet face that fooled the forecasters. Yet beneath that face, the sound waves insisted, an energy was trapped. An energy comparable in strength to cycles the surface itself never dared to imitate. The question hanging over all of it was simple and unnerving. If the energy was truly down there, hidden below the skin, where would it go? Energy does not vanish because we fail to see it. It waits. And eventually it finds a way out. The Gannon storm was one of the ways out. There is a comfortable misconception about solar storms, and it is worth taking apart slowly, because taking it apart is how you feel the true scale of what happened. Ask most people what a solar storm looks like, and they will describe the aurora, curtains of green and red light draped across a northern sky. Something beautiful, something distant, something that happens to other people in colder countries, harmless as a screensaver glowing in a dark room. That picture is not wrong, but it is the smallest and gentlest fragment of a far larger truth. The aurora is not the storm. The aurora is the exhaust. It is the faint, visible residue of an enormous transfer of energy, the portion mild enough to leak out as light rather than force. What actually arrived at Earth in May of 2024 was not a light show. It was a wave of magnetized plasma, launched from that swollen region, crossing the 93 million miles between the Sun and Earth, and slamming into the invisible magnetic shell that wraps our world. The engine of it was not a single explosion, but a barrage. Over several days, region 3664 hurled a series of coronal mass ejections toward Earth, vast eruptions of solar material flung outward at millions of miles per hour. These are not flares of light. A coronal mass ejection is a physical thing, a cloud of charged particles and tangled magnetic field weighing billions of tons, torn loose from the Sun's outer atmosphere and thrown across the solar system. Several of them departed the Sun in quick succession, and because they departed in quick succession, the later, faster clouds overtook the earlier, slower ones along the way, merging into a single reinforced front. By the time this combined wave reached us, it did not knock, it struck. Consider what this means for the air above your head, not the air you breathe, but the thin outer envelope of the atmosphere, a region called the thermosphere that begins roughly 100 miles up. On an ordinary day of high activity, the thermosphere at that altitude might reach a temperature of around 1,200 degrees Fahrenheit. During the Gannon storm, it climbed past 2,100 degrees. The outermost skin of our own planet's atmosphere was superheated by nearly 1,000 degrees in a matter of hours by energy that had originated inside a star. Not warmed gradually across a season, not nudged by the ordinary rhythm of day and night. Superheated, almost instantly, from the inside of the solar body outward to the edge of our own. And the storm did not stop at heating. It rearranged the very architecture of the space around Earth. Our planet is wrapped in two permanent zones of trapped radiation, the Van Allen belts, discovered at the very dawn of the space age. They are among the most stable features of near-Earth space. Yet during this storm, something appeared that should not have been there. Two new temporary belts of radiation formed in the gap between the permanent ones, conjured out of the chaos, holding their charge for a time before slowly fading away. For a while, the Earth wore extra rings it had never worn before. Lower down, in the electrically charged layer called the ionosphere, the disturbance bent the map itself. The dense band of the ionosphere that normally straddles the equator was pulled and warped, dragged out of its usual place, and dipping toward the South Pole in a shape that scientists described, plainly and memorably, as a check mark drawn across the sky. The invisible geography of our upper atmosphere was redrawn overnight by a force reaching up from 93 million miles away. The storm was the loudest single moment, but it did not stand alone. It sat inside a year of extraordinary violence from a sun that the forecasts had promised would stay quiet. Only 9 days after the storm, on the 20th of May, the sun released a flare of the class scientists label X12, a burst of radiation so powerful it ranked among the 10 strongest recorded since 1996. The European Solar Orbiter, a spacecraft built to stare directly at our star, caught it in the act. Then, on the 26th of July, an even greater flare erupted, an X14, larger than anything the cycle had produced to that point, though it fired from the far side of the sun, its worst fury aimed away from us. And later still, in October, a region catalogued as 3842 loosed a flare measured at X 9.05, the most powerful the world had seen in 7 years, just 2 days after that same region had already fired an X 7.1. Notice the pattern. Not one anomaly, but a sequence of them. Not a single freak storm, but a steady drumbeat of extreme events, one after another, from a star whose surface numbers had promised something mild. This is precisely why the storm mattered so profoundly to the people studying the sun's hidden interior. It was proof, written across the sky and recorded in every instrument we possessed, that the energy the sound waves had detected was real. The quiet face was a mask, and in the spring and summer of 2024, the mask slipped. But to say the mask slipped is to speak only of the sun. What the Gannon storm did next was something stranger and far more intimate. It reached past the sky and into the machinery of ordinary human life. It did not stay in the thermosphere. It did not remain a matter of belts and check marks and distant lights. It came down. It came all the way down, into fields and flight paths and orbiting metal, into the fragile web of technology on which a modern civilization quietly depends. And what it touched there is where the true weight of this hidden change begins to settle. Consider what this means. A modern civilization does not feel the sun as a distant fire hanging in the daytime sky. It feels the sun through the machinery it has built to live alongside it. The satellites that carry our voices, the signals that tell our clocks the time, the long metal arteries of the power grid that keep the lights burning through the night. Every one of those systems was designed against a sun we believed we understood. That is the quiet assumption underneath the whole modern world. And that assumption is exactly where the hidden change turns dangerous. Not because the sun has grown louder in any obvious way. The surface said the opposite. The sunspot numbers, taken at face value, described a modest and unremarkable star, but because the energy that once spread itself through the great depth of the sun is now being pressed into a shell so thin it defies intuition. A shell roughly 1,000 kilometers deep, 621 miles, on a body whose radius stretches 432,000 miles from center to surface. The activity has been driven into the outermost fraction of a percent of the star, held just beneath the skin, closer than it has ever been to the moment of escape. Here is the reframe that changes everything that came before. For most of this journey, the story has sounded like a puzzle of appearances. The sun looked calm on the outside while the sound waves reported strength within. It was tempting to hear that as a kind of reassurance, a technicality, a gap between two instruments that scientists would eventually reconcile. But the Gannon storm dissolved that comfort. The gap between the calm face and the violent interior is not a measurement error. It is the danger itself. Ask anyone whether a quiet sun is a safe sun, and they will answer without hesitation. Fewer sunspots, less risk. A weak cycle, a gentle decade. It feels like common sense. It is also wrong. Solar cycle 24 was the weakest cycle in 100 years. The minimum that followed it sank to a smoothed sunspot number of just 1.8, one of the deepest and stillest lulls in the entire modern record. By every surface measure, the sun had gone quiet in a way it had not managed in a century, and from that profound stillness rose solar cycle 25, the cycle that would produce the first severe geomagnetic storm in over 20 years. The quiet did not predict the calm. The quiet preceded the blow. This is the disturbing logic that the hidden change forces us to confront. Not that a stronger sun makes stronger storms, that much was always true, but that a sun which looks weaker on its surface can now conceal the same strength beneath it, waiting, unexpressed, invisible to the very counts we have used for centuries to read its temper. The sunspot number was our oldest and most trusted reading of the sun's mood, a record kept faithfully for generations, and the shallowing interior has quietly severed the link between that number and the truth. The surface can mislead us now. It is learned to. There is even a record of the quiet written into the sun itself. The long, deep minimum of 2008 and 2009, the stillest stretch of solar silence in the modern era, did not simply pass and vanish. It left a mark. When researchers examined the helioseismic data from the years that followed, they found the fingerprints of that silence pressed into the interior, stronger signals from the helium buried in the outer layers, sound waves moving faster through the gas near the surface, temperatures nudged slightly upward from what earlier minima had shown. Chaplin put it plainly, deep quiet minima can leave a measurable internal fingerprint. The sun remembers its own stillness, and what it does with that memory we are only beginning to learn. Think about what it means to hold that much energy so near the surface. In a deeper star, the magnetic fields would have room to rise slowly, to spread their strength across the whole convecting body, to shed some of their intensity on the long climb toward the light. Compressed into a thin outer layer, they have no such room. They are concentrated. They are held close to the place where they can break free and hurl themselves across the vast reach of empty space toward the Earth. The very confinement that made Cycle 25 look modest may be the mechanism that makes its eruptions so sharp. Not despite the shallowing, but because of it. And this is the turn that should hold your attention even as the rest of you drifts towards sleep. The single largest sunspot region of the storm, the region catalogued as 3,664, grew to an active area 17 times the diameter of the Earth. It sat on the face of a star that the official numbers had called unremarkable. A modest cycle produced a monster. The forecast had promised something mild, a smoothed peak near 115. The Sun answered with a peak of 216 and a maximum of 160.8, 40% above the prediction. And then, from that supposedly gentle maximum, it launched the largest storm in a generation. There is a fragile kind of hope buried in all of this, and it is worth naming before the weight settles fully. We are not blind to the change. That is the quiet gift of listening to the Sun the way we now do. The Birmingham Solar Oscillations Network has been turning its ears toward the star since the 1970s. 6 telescopes spread around the world, so that no matter how the Earth rotates, at least one of them is always facing the light. It hears the sun ring. It hears the sound waves that surface counts can never reveal. And so, when the visible face went quiet and the interior stayed strong, we noticed. William Chaplin and Sarbani Basu and their colleagues could stand before 40 years of data and say plainly that something had shifted since Cycle 23, that the change had begun around 2005, almost 2 full cycles before anyone possessed a tool sharp enough to catch it. But hearing a danger is not the same as understanding it. And understanding it is not the same as predicting where and when it will strike. This is the harder truth folded inside the hope. We can now detect that the Sun is reorganizing itself. We cannot yet explain why. Basu was careful to say that the trend cannot be blamed on weaker magnetic fields, that it points instead to a structural reorganization of how the Sun stores its magnetic activity beneath the surface. That sentence describes a change. It does not describe a cause. No settled physical model predicted that the Sun's activity would migrate steadily upward, cycle after cycle, toward the skin of the star. The instruments found it first. The theory is still running to catch up. So we are left in a strange and unfamiliar position. We have built a civilization that leans its whole weight on the assumption of a predictable Sun. We have discovered, using the finest ears we have ever turned toward a star, that the Sun is quietly rewriting the rules by which it behaves. And we have watched, in a single week of the spring of 2024, what happens when that hidden strength finally speaks. The storm did not announce itself in the sunspot count. It did not warn us through the ordinary channels. It rose from a face we had judged to be calm, and it came down. That is where the true reckoning begins. Because a storm in the thermosphere is a distant thing, a matter of physics unfolding 100 miles above our heads, something we can read about and marvel at and forget. But the Gannon storm did not stay 100 miles up. It descended into the systems that ordinary life now takes for granted, the ones no one thinks about until they falter. Into the fields where machines steer themselves by signals from space, into the flight paths that arc across the high latitudes, into the thin metal shells circling the Earth in their thousands. The hidden change inside the Sun stopped being an abstraction the moment its consequences touched the ground. Consider what this means. Across the American Midwest, in the season when the soil is turned and the year's food begins, farmers sat inside cabs that no longer knew where they were. The machines had not broken. Nothing mechanical had failed. The engines ran. The blades turned. The fuel held steady in the tanks. But the tractors that steer themselves by signals from orbit had lost the thread of those signals, and so they wandered from their rows, or they slowed, or they simply stopped in the middle of a field with nowhere left to go. This is the strange intimacy of the age we live in. A magnetic disturbance born beneath the surface of a star reached down through the vacuum in the atmosphere and the pale morning light and pushed a plow off its line in the soil of Iowa. It did this not through heat and not through radiation. It did it through the quiet corruption of a timing signal that farming had come to lean upon, without ever noticing the weight of that dependence. The average loss reached $17,000 for each farm the storm touched. A single planting window, narrow and unforgiving, disrupted not by drought or frost or any enemy a farmer has ever learned to read, but by the interior weather of the sun. Consider how quietly that dependence had been built. No one ever designed the modern grain harvest to hang upon the magnetic mood of a layer beneath the solar surface. And yet it did, and the storm revealed it in an afternoon. The disruption did not stop at the edge of the field. High above the North Atlantic, the flights that arc across the top of the world were pulled southward, rerouted onto lower tracks to escape the radiation and the communication blackouts that bloom over the poles whenever the sun grows loud. On the ground, high-voltage power lines tripped as surging currents ran through wires never meant to carry them. Transformers, the heavy iron hearts of the electrical grid, overheated at their posts. These are not delicate instruments. They are among the most robust machines humanity builds, engineered to stand for decades against storms of the ordinary kind. But the storms of the ordinary kind rise from our own atmosphere. This one rose from somewhere else entirely. And then there were the satellites, the thin metal shells we have hung in their thousands just above the sky. When the Gannon storm struck, the Earth's upper atmosphere did not merely warm. It swelled, heated far beyond its usual state. The thin gas of the thermosphere expanded outward and climbed, reaching up into the orbits where our machines circle, thickening the emptiness they had been built to glide through. And so thousands of satellites, moving at many thousands of miles per hour, suddenly met resistance where they had expected almost none. NASA's ICES at 2, a satellite built to measure the ice of a warming world, lost altitude and slipped into safe mode, shutting down its instruments in order to survive. The storm shoved it toward re-entry by roughly 11 days, stealing 11 days of its working life in a single event. A smaller craft, the Serb CubeSat, fared worse. It fell from orbit 5 months ahead of its time, dragged down and burned away by an atmosphere the sun had briefly inflated. Now consider the scale of what moved. Of the roughly 10,000 satellites circling in low orbit around the Earth, approximately half performed coordinated avoidance maneuvers during the storm, firing their thrusters, adjusting their paths, shifting to keep from colliding in the suddenly crowded and suddenly thickened sky. It was the largest satellite migration event ever recorded. Not the largest of the year, not the largest of the decade. The largest that has ever been recorded in the entire history of spaceflight. Roughly 5,000 human-made objects moving at once, not because their operators had willed some grand maneuver, but because the interior of the sun had exhaled, and the exhalation had reached all the way up to them. And while the machines struggled, the sky above the whole world began to burn with colour. The Gannon storm generated more than 6,000 reports of visible aurora, gathered from 55 or more countries, from every single one of the 7 continents. Light that ordinarily crowns only the far north and the far south spilled down toward the middle of the Earth. Auroras were seen at 26 degrees of magnetic latitude, a reach so far from the poles that it may rank among the lowest latitude sightings in 500 years. 500 years. The last time the sky may have glowed this far toward the equator, no one alive today had yet been born, and few who witnessed it left a record we can trust. Over Japan, observers watched the air turn magenta at an altitude of roughly 600 miles, far above the ceiling of 400 miles, where the red aurora is normally free to climb. The light itself was reaching higher than the light is supposed to reach. Nor was the Earth the only world the sun touched that spring. On the 20th of May, in the same convulsive stretch of weeks, an X-12 solar flare erupted, and its radiation crossed the tens of millions of miles to Mars. NASA's Curiosity rover, crawling across the rust-coloured plains, registered a surge of radiation equivalent to roughly 8,100 micrograys. For a hypothetical astronaut standing unshielded on the Martian surface, that dose would have been comparable to about 30 chest X-rays absorbed in a matter of hours. And from the 14th to the 20th of May, the MAVEN spacecraft watched auroras ignite across the entire face of Mars, a planet that lost its global magnetic shield long ago and so glows all over rather than only at its poles. The same interior violence that crippled tractors in Iowa lit up a world with no one to see it. Not one planet. 2. The reach of a single restless sun. Consider what all of this tells us, and consider it slowly, because it is the heart of the matter. Everything described here, the crooked furrows, the rerouted flights, the tripped transformers, the falling satellites, the migrating fleet, the magenta sky over Japan, the glowing air of another planet. All of it came from a sun the surface indicators had judged to be running an ordinary, even a modest cycle. The sunspot count did not warn us. The radio flux did not warn us. By the measures we have trusted for generations, this was not supposed to be a sun capable of such a week. And yet the energy was there all along, held in the shallow layer just beneath the visible surface. In the reorganized architecture the sound waves had already revealed. The storm was not the anomaly. The storm was the anomaly made visible. Now extend that thought across time, because this is where the quiet dread settles in. We have watched the sun through instruments for only a handful of generations. The listening network has been gathering its measurements for a matter of decades, and even that brief span of attention has caught the interior in the act of changing. But the sun does not measure its life in decades, it measures it in billions of years. What we have glimpsed is not a single event but a direction, a trend that has held across 4 consecutive cycles and shows no sign of reversing. And we do not know where the trend leads, not because the mathematics lie beyond us. The equations of the solar dynamo are written down, studied, simulated on the largest machines we possess, but because every honest attempt to carry those equations forward across the coming decades arrives at the same quiet place. The honest answer is that nobody knows. This is the reality that everyday experience conceals from us. To stand in a field on a spring morning is to feel the sun as a fixed thing, a constant, the one light that has risen over every day of every human life without a single exception. Nothing in the ordinary sensation of warmth on the skin suggests that the star above is a churning, restless body, remaking its own inner structure on a scale we have only just become able to measure. The steadiness we feel is real, but it is the steadiness of a single glance at something vast and slow. It is the steadiness of one frame drawn from a film that runs for 10 billion years. Not the steadiness of a thing that does not change, but the steadiness of a change too large and too gradual for a human lifetime to notice. And that is the discomfort hidden inside the comfort. We are not troubled by the sun because we have never been given a reason to be. Every generation before us inherited a sun that behaved, and passed down a sun that behaved, and the sheer regularity of it became invisible, the way the ground beneath your feet becomes invisible until it moves. The Gannon storm was the ground moving. For a single week, the star stopped being a backdrop and became an actor, reaching into the systems we had quietly built our entire civilization upon, and reminding us that the calm we depend on is not a promise. It is only a pattern. And a pattern, by its nature, is a thing that can change. So the question grows heavier the longer you hold it. If the interior of the sun has been reorganizing itself for the better part of 2 decades, unseen, unmeasured, and if a sun the instruments called modest could still summon the largest satellite migration in history, then what, exactly, are we watching the beginning of? The shallowing did not stop at cycle 25. Nothing in the data suggests a flaw, and beneath even that unresolved trend lies a deeper layer still, a region so far down and so strange that the scientists who study it have only just begun to model it at all. That region has a name. The scientists who study the sun call it the tachocline. and it is one of the strangest places in our entire solar system, though no eye will ever see it and no probe will ever reach it. It sits about 7/10 of the way out from the center of the Sun, buried beneath roughly 200,000 kilometers of superheated plasma. To place that depth in human terms, consider that the layer we have been circling all this time, the shallowing magnetic activity now confined to within 621 miles of the visible surface, is a skin. The tachocline is not the skin. It is something closer to the spine, not the crust of the Sun, not the visible surface where the sunspots bloom and fade, not even the vast churning convective ocean that carries heat upward for hundreds of thousands of miles. The tachocline lies beneath all of them, at the boundary where two utterly different worlds meet and refuse to move at the same speed. Above it, the outer third of the Sun behaves like a fluid, turning faster at the equator than at the poles, a body of plasma that rotates in pieces rather than as a whole. Below it, the deep interior turns rigidly, all of it locked together, spinning the way a single solid object spins. Between these two mismatched motions lies a thin shearing seam. This is the tachocline. It is the place where the Sun grinds against itself. And here is the reason it matters. Many solar physicists believe this thin, violent boundary is where the Sun's magnetic field is born. This distinction matters enormously, because everything we have described so far, the storms, the flares, the vanishing poles, the shallowing skin of confined activity, may all be surface expressions of a process that begins in this hidden seam. The tachocline is the suspected forge. Everything else is sparks. For decades this was educated speculation. The tachocline is impossibly remote. It cannot be sampled, cannot be photographed, cannot be reached by any instrument humanity has ever built or is ever likely to build. It could only be inferred. Then, in 2025, that began to change. A team at the University of California, Santa Cruz, led by Lauren Matilski, working alongside Nicholas Brummel and Lydia Corey, published a study in the astrophysical journal Letters, describing the first self-consistent computer simulations of the solar tachocline ever produced. The phrase to hold on to is self-consistent. Earlier models had to assume certain things to make the mathematics behave. This one did not. Consider what it took. The computations required tens of millions of supercomputing hours on NASA's Pleiades supercomputer, running for 15 months to resolve a single layer inside a single star. 15 months of one of the most powerful machines our species has ever assembled, spent listening not to the wider universe, but to the interior logic of the one star at the center of our own sky. And what the simulation revealed was a loop. The tachocline drives the solar dynamo, the vast engine that generates the Sun's magnetic field. But the dynamo, in turn, produces magnetic forces that reach back and hold the tachocline thin, pressing it into the narrow seam it occupies. Not a one-way street from cause to effect. A circle. The layer creates the magnetism, and the magnetism sculpts the layer, each one shaping the other in a feedback that had never been captured self-consistently in any model before. Now sit with what that circularity implies. If the magnetic activity at the surface is reorganizing itself, squeezing into an ever shallower skin cycle after cycle, and if that surface magnetism is bound in a loop with the deep engine that produces it, then a change we can see at the top may be the visible edge of a change we cannot see at the bottom. The skin and the spine are not independent. They are two ends of the same conversation. And the honest answer is that nobody knows which end is speaking first. The uncertainty runs deeper still. Even now, even after 15 months of supercomputing, the exact location where the solar dynamo primarily operates remains disputed. Some researchers place it in the near-surface shear layer, close to the top. Some spread it throughout the entire convection zone. Some place it precisely at the tachocline, down in that grinding seam. We have modelled the machine more faithfully than ever before, and we still cannot say for certain where inside it the fire actually starts. Consider what this means across deep time. The Sun has been running this hidden engine for roughly 4.5 billion years. It will run it for billions more. And in the vanishingly thin sliver of that history, during which human beings have possessed instruments sensitive enough to listen, we have caught the interior in the act of changing. The relationship between the Sun's inner oscillations and its outer activity shifted around 2005. The magnetic skin has been thinning across 4 consecutive cycles, and the engine that ties these together turns in a place we have only just learned to simulate at all. The surface has been giving its own quiet warnings. In 2024, the Sun's magnetic poles reversed their polarity, as they do near the peak of every cycle. The northern polar cap above 70 degrees flipped around November of that year. The southern cap flipped around October, but before they flipped, both poles weakened to almost nothing. Lisa Upton of the Southwest Research Institute described watching the fields drain away. "They are getting really close to zero," she said. "They are getting very, very weak. Not weak in the ordinary sense. Not the gentle ebb of a field settling toward a turning point. The poles approached a genuine vanishing, a near total collapse of magnetic charge at both ends of the star before the new polarity emerged, and the recovery has not been symmetric. The northern polar field is predicted to decline sharply until March of 2026, driven by active regions carrying the wrong polarity, becoming, in the language of the forecasts, exceptionally weak. The Sun is not returning to balance in an orderly way. It is lurching. This lopsidedness is not entirely without precedent. Cycle 24, the weakest cycle in 100 years, showed its own strange asymmetry, a lag of roughly 16 months between the reversal of its northern and southern hemispheres. The two halves of the Sun fell out of step by more than a year. What we are seeing now is not a single anomaly standing alone. It is the latest entry in a lengthening list of ways the Sun has begun behaving unlike the Sun we thought we understood. And every one of these threads runs downward. The vanishing poles, the lurching recovery, the confined skin, the trapped energy that never became sunspots, the internal frequencies that shifted almost 2 decades ago. Pull on any single thread and the line disappears into the same dark region, that grinding seam 200,000 kilometers beneath your feet, where the field is forged and the machine turns in a loop we have barely begun to model. Everyday experience insists the Sun is a fixed thing, a constant, the one light in all the sky we can count on without thinking. The mathematics quietly disagrees. The mathematics describes a dynamic system balanced on feedback so intricate that we cannot yet name the place where its central process lives. We built our entire world on the assumption of a steady star. Nothing in the physics ever promised us one. And the further we follow these threads down toward that deepest layer, the clearer it becomes that the strangest part of this story is not the storms we have already weathered, nor the records we have already broken, but the single unanswered question still waiting at the very bottom of the light. Consider where that final question actually lives. It does not live in the light we can see. It does not live in the sunspots we can count, or in the flares that announce themselves the instant their radiation reaches us. It lives in a place no telescope will ever photograph, a thin and violent boundary buried roughly 7/10 of the way from the Sun's center to its surface. This is the region the previous threads all pointed toward. Scientists gave it a name that sounds almost gentle. They call it the tachocline. The tachocline is a shear layer, and to understand why it matters, you have to picture 2 utterly different motions meeting in a single seam. Above it, the outer third of the Sun churns and boils in enormous overturning cells, and this outer envelope rotates faster at the equator than it does near the poles, the way a fluid moves when nothing forces it to turn as one solid piece. Below it, the deep interior rotates rigidly, like a ball of stone, every part keeping perfect pace with every other part. Between those two behaviors lies the tachocline, a boundary only a fraction of the Sun's width, where the churning outer layer grinds endlessly against the rigid core beneath. It is a place of tremendous stress, and most physicists believe it is where the Sun's magnetic field is actually forged. That belief has been the foundation of solar physics for decades. Yet here is the quiet embarrassment at the center of the field. Until very recently, no one had ever built a working model of the tachocline that held together on its own terms. The layer was too deep to observe directly, too complex to simulate honestly, and too important to ignore. So it sat in every textbook as a kind of promissory note, a structure we were certain existed and certain mattered, described in careful words but never truly reproduced. The sun kept its most important machinery in the one place we could neither see nor faithfully compute. That began to change in 2025. A team at the University of California, Santa Cruz, led by Lauren Matilsky and working with Nicholas Brummel and Lydia Corey, published in the Astrophysical Journal Letters the first self-consistent computer simulations of the solar tachocline. The word to hold on to there is self-consistent. It means the model was not told in advance how the layer should behave. It was allowed to generate its own structure from the underlying physics, and then watch to see whether that structure survived. The computation was staggering in its cost. It required tens of millions of hours of supercomputing time, run on NASA's Pleiades machine over the course of 15 months. 15 months of relentless calculation to reproduce a sliver of a star, and what the simulation revealed was not a simple answer. It was a loop. The team found a reciprocal relationship that had never been modeled self-consistently before. The tachocline drives the solar dynamo, the great engine that generates the sun's magnetic field, but the dynamo's own magnetic forces reach back and actively hold the tachocline thin, pressing that grinding seam into the narrow band it occupies. The layer creates the field disciplines the layer. Each one is both cause and consequence of the other, locked in a feedback so tightly wound that you cannot pull the two apart and study either one alone. This is not a chain of events with a beginning and an end. This is a circle that has been turning for billions of years. Consider what that means for anyone trying to predict this star. A system built on feedback does not respond to a single push in a single traceable way. Nudge one part of it, and the effect races around the loop and returns transformed, sometimes amplified, sometimes reversed. The behavior we have been watching at the surface, the trapped energy, the shallowing activity, the storms that arrived from a cycle that was never supposed to be strong, may all be the loop expressing a change deep inside itself. Not a change we caused, not a change we can steer, a change in the internal balance of a machine we have only just learned to imitate for 15 months at a time. Here is the problem that lies beneath even that. The tachocline simulation was a triumph, and it deepened the mystery rather than closing it, because the most basic question of all remains unsettled. Scientists still do not agree on where the solar dynamo primarily operates. Some argue it lives at the tachocline itself, down at that deep boundary. Others argue it works throughout the entire convection zone, spread across the whole churning outer third of the sun. Still others place its main action in a near-surface shear layer, far shallower, much closer to the light we actually see. This is not a minor disagreement about details. This is uncertainty about the location of the single most important process in the star that governs all life on Earth. And now, hold that dispute beside the discovery that opened this entire story. The helioseismic data showed that the sun's magnetic activity has been squeezed into an ever shallower layer with each passing cycle, until it now sits within roughly 1,000 kilometers of the visible surface. The dynamo's location is disputed between the deep and the shallow, and the activity itself appears to be migrating toward the shallow. No one has proven that these two facts are the same fact. But the shape of the question has changed. We are no longer only asking why the sun is behaving strangely. We are asking whether the very place where its magnetism is born might itself be shifting, quietly, upward, toward the surface, inside a feedback loop we have modeled exactly once. To feel how young this understanding is, consider the raw arithmetic of it. The sun has been burning for roughly 4.5 billion years. Human beings have possessed the tools to listen to its interior for only a few decades. and we have possessed a self-consistent model of its central magnetic engine for a matter of months. If the entire life of the Sun were compressed into a single year, our first honest simulation of its core machinery would have arrived somewhere in the final fraction of the final second before midnight. We are reading the opening line of a book that has been writing itself since before the Earth existed. Now consider what the Sun did with its poles while all of this was being worked out, because this is where the strangeness turns almost personal. Every 11 years, near the peak of its cycle, the Sun reverses its magnetic polarity. Its north pole becomes its south, and its south becomes its north. This is normal. This is the heartbeat of the star. But in 2024, as the reversal approached, both poles did something that made researchers watch very closely. They did not simply flip. They first weakened almost to nothing. The southern polar cap reversed around October of 2024, and the northern cap, above 70 degrees of latitude, reversed around November. Before each flip, the field there had drained toward zero. Lisa Upton of the Southwest Research Institute described it plainly. "They are getting really close to zero," she said. "They are getting very, very weak." A magnetic pole approaching zero is not a catastrophe on its own. It is part of how the reversal works. But the way this reversal is unfolding is not symmetric, and the asymmetry is the unsettling part. After the flip, the northern polar field is predicted to keep declining sharply, driven by active regions surfacing with the wrong polarity, until it becomes exceptionally weak around March of 2026. One hemisphere of the Sun is behaving very differently from the other. This is not the first time the star has fallen out of step with itself. The previous cycle, cycle 24, carried its own anomaly, a lag of some 16 months between when its two hemispheres reversed, as though the two halves of the Sun were no longer keeping the same time. Consider what that image really contains. We tend to picture the Sun as a single, unified object. One sphere, one glow, one steady thing hanging in the same place it has always hung. The physics is beginning to describe something else. It describes a star whose northern and southern halves can drift apart in their rhythm, whose central engine may be relocating toward its own surface, whose deepest layer turns in a feedback loop we have simulated exactly one time. Not a fixed lamp, not a constant. A vast and layered machine that is in several independent ways at once, quietly departing from the behavior we assumed was permanent. And this is the honest place to stand at the bottom of the light. Not in despair, and not in false comfort. The truth is genuinely balanced on a knife's edge. On one side sits a real and hard-won hope. For the first time in the history of our species, we can listen to the interior of a star and hear its structure change. We can model the seam where its field is made. We built a network of 6 telescopes across the whole rotating Earth and used the Sun's own sound to see inside it. And it worked. That is not a small thing. That is one of the quietest and most extraordinary achievements human beings have ever managed. On the other side sits the new dread, and it is not the dread of a coming disaster. It is subtler, and in its way, larger. It is the dread of realizing how little the achievement has actually settled. We can hear the change and we cannot yet explain it. We can model the loop and we cannot locate its center. We can watch the poles vanish and reappear out of step, and we have no theory that predicted any of it in advance. The more precisely we have learnt to look, the more clearly we have seen that our confident, comfortable picture of a steady Sun was never a conclusion of the physics. It was only an assumption we never thought to question, because the star had never before given us a reason to. And so we arrive at the deepest layer of the unknown, the one that sits beneath all the others. To understand why the Sun's magnetism might be migrating toward the surface, you have to understand where that magnetism is thought to be born. And that birthplace is a region so remote and so strange that until very recently no one had ever modelled it honestly. It is called the tachocline. The name is unfamiliar because the thing itself is hidden from every instrument we have ever built. No telescope will ever photograph it. No probe will ever fall through it and survive. We know it exists only because the sun's sound waves bend as they pass through it, the same way the BiSON network learned to listen to everything else. The tachocline is a shear layer roughly 200,000 kilometers deep, sitting about 7/10 of the way out from the sun's center toward its surface. To give that number a body, imagine lining up more than 15 Earths side by side. That is the thickness of a single transition zone buried inside a single ordinary star. Above it lies the convective envelope, a churning ocean of plasma that rotates faster at the equator than at the poles. Below it lies the radiative interior, which turns rigidly, all of one piece, like a solid ball of light. The tachocline is the seam where these two utterly different motions grind against each other, and most physicists believe that this seam, this thin and violent boundary, is where the sun's magnetic field is generated. For decades, this was a story we told without being able to prove it. The mathematics were too difficult. The scales were too extreme. Then in 2025, a team at the University of California, Santa Cruz, led by Lauren Matilsky, working with Nicholas Brummel and Lydia Corey, published in the astrophysical journal Letters the first self-consistent computer simulations of the solar tachocline ever produced. The words to hold on to there are self-consistent. They mean the simulation was not told in advance how the layer should behave. It was allowed to find its own balance from the underlying physics. That achievement did not come cheaply. The computations required tens of millions of supercomputing hours on NASA's Pleiades machine, running for 15 months. And what they found was a loop, not a simple chain of cause and effect, but a circle that closes on itself. The tachocline drives the solar dynamo, the great engine that generates the star's magnetic field. But the dynamo, in turn, produces magnetic forces that reach back down and hold the tachocline thin, pressing that violent seam into the narrow band where it sits. Each one sustains the other. Neither can be understood alone. It is a feedback loop that had never before been modeled in a way that let both halves speak to each other at once. For the first time, we could watch the sun build the very structure that builds the sun. This is the tiny hope inside the deepening dread. We now have a working picture of the machine, or at least a piece of it, running honestly inside a computer. That is real progress, hard-won and beautiful. But hold the hope loosely, because the same research that gave it to us also admits what it cannot yet settle. The exact location of where the solar dynamo primarily operates remains genuinely disputed. Some models place it at the tachocline, deep and hidden. Others place it throughout the whole convection zone. Others still place it in a shallow shear layer just beneath the surface. And you may notice, if you have been listening closely, that this last possibility rhymes uncomfortably with everything the BiSON data has been telling us. The magnetism is confining itself to the outermost 1,000 kilometers, and we do not know for certain whether that is where it was ever truly made. Consider what this means. We have discovered that the sun is reorganizing where it keeps its magnetic activity, and in the same decade we have discovered that we were never entirely sure where that activity comes from in the first place. The two mysteries are not separate, they are the same mystery, seen from two directions. The star is changing the answer to a question we had not finished asking, and there is one more thread to draw into this, the strangest of all. In the year 2024, the sun's magnetic poles reversed, as they do near every solar maximum, north and south trading their polarity. But they did not do it together. The southern polar cap reversed first around October. The northern cap followed around November. Before each flip, the fields did not simply swing from one sign to the other. They weakened almost to nothing. Lisa Upton of the Southwest Research Institute described it plainly. They were getting really close to zero, she said. Getting very, very weak. That vanishing is expected. What is not expected is what comes next. The northern polar field is predicted to keep declining sharply, becoming exceptionally weak, held down by clusters of active regions carrying the wrong polarity. And this decline is forecast to continue until around March of 2026. It is a lopsided, asymmetric behavior, one hemisphere out of balance with the other, and it echoes the previous cycle, which carried its own strange asymmetry, a lag of some 16 months between the moment the northern hemisphere reversed and the moment the southern one did. The sun's two halves, it seems, are no longer keeping perfect time, so gather the threads. A magnetic layer squeezing itself toward the surface across 4 consecutive cycles, a hidden strength in cycle 25 that the sunspots refused to show. An internal shift that began around 2005, silent and invisible for years. A dynamo whose birthplace we cannot agree on. A pair of poles that vanish out of step and return unbalanced. Each of these was measured carefully, by careful people, with instruments of extraordinary sensitivity, and not one of them was predicted. Not one of them was foreseen by any theory we hold. We built the tools that could finally see the change, and the change they revealed was that we understand our own star far less than we believed. Ask the researchers what it all means, what the sun is becoming, where this reorganization is carrying us, and the most truthful voices give the same reply. The honest answer is that nobody knows. Not yet, perhaps not for a long time, and that is where the science, for now, must leave us. Standing at the edge of a question far larger than the star that raised it, there is a particular quiet that arrives at the edge of a question like this. It is not the quiet of an answer. It is not the settled silence of a problem solved and set gently aside. It is the quiet of standing before something that refuses to resolve, something that keeps its shape no matter how long or how carefully you look at it. For 4 consecutive cycles now, our star has been quietly rearranging the way it stores its own strength, pressing its magnetic activity into an ever shallower layer beneath the surface. And the people who study it most closely have told us plainly that they do not yet understand why. That admission is not a failure. It is, in its own strange way, the most honest gift that science can offer, not the false comfort of certainty, but the deeper comfort of a truth spoken without pretense. Consider what that truth actually asks of us. We live beside this star. Every warmth you have ever felt on your skin, every green and growing thing, every calorie your body has ever burned, traces back through an unbroken chain to the light of a single sphere, 432,000 miles in radius, burning quietly at the center of everything we are. It has been there for the whole of human history. It rose before there were eyes to see it rise, and for all of that time, we assumed we knew its nature, that it was the one constant we could lean against, the one thing in the sky that would behave tomorrow the way it behaved yesterday. Now the sound waves moving through its interior have told us otherwise. The change is real, the change is measured, and the change was never predicted by any theory we hold. Sit with the shape of that for a moment. The magnetic engine that drives the storms and the auroras and the flares has drawn itself inward until it lives within roughly 1,000 kilometers of the visible surface. 621 miles. On a body that spans hundreds of thousands of miles, that is the thinnest imaginable skin, the outermost fraction of a percent of the whole, and the shift that carried it there began around 2005, silent and undetected, unfolding for the better part of 2 full cycles before any instrument on Earth was sensitive enough to notice. The sun was changing while we watched it, and we could not see the change. The tools that finally revealed it are the same tools that revealed how little we understood in the first place. This is the humbling that sits at the heart of the discovery. Not a humbling of despair, a humbling of proportion. For centuries we have told ourselves a certain story about knowledge, a story in which understanding advances steadily, in which each generation hands the next a more complete map, in which the great mysteries are slowly filled in like blanks on a page, and there is truth in that story. But the sun has just written a different sentence into it. It has reminded us that the object closest to us, the object our entire existence depends upon, the object we have watched more continuously than any other in the sky, still holds behaviors we did not know were possible. If we can be surprised by our own star, we should be gentle with ourselves about everything further away. So what do we do with a question that has no answer yet? This is where the science, honest to the end, hands the question back to us. And here the two possible readings of it open like two doors in the same wall. Perhaps this reorganization is nothing to fear. Perhaps the sun has done this many times across its long life, drawing its strength inward and letting it out again in slow rhythms that stretch across centuries, patterns far longer than any human record, invisible to us only because we arrived so recently and watched for so short a time. Perhaps the deep quiet of the minimum between the last two cycles, the quietest on record, left its fingerprint inside the star, the way a hard winter leaves rings in a tree, and what we are seeing is simply the star remembering, the slow arithmetic of a system far older and far more patient than our instruments. Perhaps in 100 years, this will read as an ordinary chapter in an ordinary life, and the alarm we feel now will seem like the alarm of a child who has never seen the tide go out and fears the sea is leaving forever. Or perhaps not. Perhaps this is genuinely new. Perhaps the shallowing we have measured across 4 cycles is the opening of a mode of behavior our species has never witnessed. A threshold the sun is crossing for the first time in all the years that anyone has been keeping count. The last cycle was the weakest in 100 years, and from those ashes the current cycle erupted with a ferocity that broke every forecast, peaking 40% above what the panel predicted and arriving 9 months ahead of schedule. The energy did not vanish. It went somewhere. It hid beneath the surface and expressed itself not as the modest sunspots we counted, but as flares among the most powerful ever recorded, and as a storm that reached down and moved half of everything we have placed in orbit. If a star can hide that much strength from our oldest measurements, we cannot honestly promise ourselves that we know what it will do next. The unsettling thing is that both readings rest on the very same facts, the same numbers, the same sound waves, the same 40 years of listening. Not because the science is weak, but because the science has reached the exact edge of what 40 years can tell us. A star does not live on a human timescale. It lives on a timescale that swallows civilizations whole. To ask whether 4 cycles of shallowing is a passing fluctuation or a permanent turn is to ask a question that 4 cycles simply cannot answer. We would need to watch for centuries. We would need generations of instruments handed down like heirlooms. We are, in the truest sense, reading the opening line of a sentence whose ending will not be spoken in our lifetimes. And that is a strange inheritance to sit with, because you cannot resolve it by thinking harder. You cannot reason your way to which door is the true one. The people who have devoted their careers to this star, who have built the networks and gathered the decades of data, and modeled the shear layer 200,000 kilometers down where the dynamo may be born, will tell you the same thing if you press them honestly. Nobody knows. Not yet. Perhaps not for a long time. The most rigorous minds in the field have arrived, together, at the edge of the same not knowing, and they have had the courage to say so out loud. These questions have no universal answers. Different people will hold them in different ways, and each way is legitimate. Some of you, hearing all of this, will feel a quiet unease settle into your chest, a small cold awareness that the ground beneath our certainties is thinner than we thought, that the star we trusted has secrets still. That response is reasonable. It is honest. There is something genuinely sobering in learning that the source of all our warmth is doing something we cannot explain. And others of you will feel something almost opposite, a kind of relief, even a kind of peace. Because if the universe were fully known, if the last mystery had been mapped and measured and filed away, there would be nothing left to wonder at. The not knowing is what keeps the sky worth looking up into. The unanswered question is not a wound. For some, it is the whole point. Neither response is wrong. They are two ways of standing beside the same fire. You do not have to choose between them tonight, and perhaps you never will, because the truth is large enough to hold both. The sun can be, at once, the thing that unsettles us, and the thing that comforts us. It can be a warning and a wonder in the same breath. The same star that hid its strength and broke its forecast, and reversed its poles out of step, and drew its magnetism into a skin thinner than the thickness of a coin against a wall. That same star still rises every single morning, still pours its light across the oceans, still holds the whole family of planets in a grip nothing has loosened in billions of years. It has not stopped being reliable. It has only stopped being simple. And maybe that is the quiet lesson underneath all of it. That reliability and mystery are not opposites. That you can depend completely on a thing you do not fully understand. You depend on your own heartbeat, though you have never once instructed it to beat. You depend on the turning of the planet, though no hand of yours keeps it turning. And you depend on this star, this changing, reorganizing, unpredictable star, whether or not any theory can yet explain what it is becoming. The dependence was never built on understanding. It was built on constancy. And the constancy, so far, remains. So we are left where the honest researchers leave us, standing beneath a star we have just learned we do not know as well as we believed, holding a question far larger than any single lifetime can close. And the only real choice before us now is not what to conclude, because there is nothing yet to conclude. The only choice is how to stand here, at the edge of the not knowing, with the warmth still falling on our faces and the answer still somewhere out ahead of us in the dark. Perhaps this is nothing. Perhaps the sun has done exactly this many times before, across the long centuries when no instrument on Earth was sensitive enough to hear it, and the reorganization now squeezing its magnetism into that thin outer skin, barely 621 miles deep on a body whose radius runs 432,000 miles. Is only one more turn of a wheel far older than any watcher, or perhaps we are the first humans ever to catch a star in the act of becoming something new. Both of these can be true at once. That is the strange gift of standing this early. The honest answer is that nobody knows. Not the researchers in Birmingham, not the modelers at Yale. Not a single instrument in orbit can yet tell you which of those two stories you are living inside. And so the question passes to you, not because you can answer it, because you cannot, and neither can anyone now alive, but because you happen to be here, in the one narrow window of time when this was first noticed at all. These questions have no settled answers. Different people will carry them differently. Some will feel a quiet unease, and some will feel a quiet wonder. And both of those responses are honest, and both are earned. What you do with the not knowing is yours alone. No scientist can decide it for you. No account of sound waves and shallow layers can close it on your behalf. So step back one last time. Step back as far as it is possible for a mind to step. This same star, the one quietly rearranging itself beneath a skin thinner than a fraction of its width, is not a small thing. And its reach is not small either. In the spring of 2024, a single eruption from its surface crossed the entire distance to Mars, washing a rover in radiation and lighting auroras across a second world at the same time our own skies burned green and red. Auroras fell that season to 26 degrees of magnetic latitude, possibly the lowest such glow in 500 years. One star did all of that. One star reaching across tens of millions of miles of empty dark, touching two planets in a single week. And that same star, that vast and casual engine, is the one now changing in ways no equation predicted. Here is the promise, and it is not a promise of despair. To live at the moment a mystery opens is not a curse. It is one of the rarest privileges a conscious creature can be handed. Generations before us looked up at a sun they believed they understood. You look up at a sun that has just confessed it has been keeping a secret for at least 20 years, since around 2005, when the changing began. That is not a loss. That is an invitation. The universe has not grown smaller with this discovery. It has grown larger and stranger and more alive with unanswered things. And you are here, awake enough to feel it, small enough to be humbled, and just large enough to wonder. So let the wonder be the last thing you hold before sleep. The sun will rise tomorrow whether or not we understand it. It will pour its warmth across your window whether or not any model can say what it is becoming. And somewhere beneath that warmth, deep in a layer we have only just learnt to listen to, a star is quietly writing the next chapter of a story that began long before us and will continue long after. The star is changing, and we do not yet know into what, but the warmth still falls, still faithful, still ours.